All right, guys, this is our first notes video. We're going to have a lot of notes like this throughout the year. So the idea behind this is that you're going to follow along with some new concepts here, and then when we get to class, on the back, we'll do some practice with these skills, all right? So make sure that you take the time to understand what we go through today in this video, and then that'll make tomorrow go a lot quicker. So the point of today's lesson is that we're going to do a few things. One thing we're going to do is determine any local extrema, and we'll explain what that means, of a function. We're going to determine the exact value of any of the roots. Roots is something you should be familiar with of a function, and we're going to classify the concavity of a function over a given interval. So we're going to talk a little bit about concavity, but these are going to be the two big ones. So going to roots. The roots of a function, as I'm sure you recall, are any point where the function touches the x-axis. So for instance, this would be one of our roots right here. This function doesn't actually touch the x-axis anywhere else, so it doesn't have any other real roots, but we will talk later about some other different types of roots that it has. But what we're going to say is that it does have a real root. And where is this real root? That's an at symbol there. It's tough to see exactly where it's at, so I'm just going to make a point, call it A, and we'll say that it has a root at x equals A. It's probably like 3.4 or something like that, but we'll just be specific. The Y-intercept. Y-intercept is just where the function touches the y-axis. So it looks like we're touching the y-axis right there, and that is at 5 on the y-axis. So the y-intercept is y equals 5. All right, nothing new yet. Now when we're talking about critical values, what I'm talking about, that's the same thing as when I mentioned local extrema. I'm talking about two specific things in this case. I'm talking about roots. Roots are critical values. And I'm talking about maximums and minimums. Those are also critical values. And extrema, because they're extreme points where something really unique is happening to that function. So when we talk about maximums and minimums, it's important to make a distinction between absolute maximums and minimums and local maximums and minimums. If you take a look at the graph here, and I'll just put an end on it, this thing probably goes forever and ever. It's just a graph that I cut out of Desmos. But usually these graphs will continue forever, so they should have arrows on the ends of them. So this graph would continue forever, which means technically it doesn't have an absolute maximum, because if we say that this is the maximum point, well, that's not true, because if we continued in the negative x direction, it would go further and further upward, right? So it would get higher and higher and have larger and larger values. So there really is no absolute maximum. But what we can say is that there's a point where it does have a local maximum, which means it's a point where it peaks. So if you want to make a note there, that maximum is just a peak, and a minimum then would be just a valley. Point where it kind of sinks down. So if I'm going along the function here, it's decreasing, and all of a sudden I hit a turning point, I hit a valley. That is a local minimum, because it's a minimum point on the graph where the function turns. So we'll say it does have a local min at the point 0, 5, because that is this point. That's the point where it's turning around at the point 0, 5. And then we keep traveling along the function, and we notice that it turns again. It gets to this peak. That's a peak at the point 2, 9. So it has a local max at 2, 9. Big key in this lesson is those two things when we're talking about critical values and local extrema. Maximums and minimums, and roots. And there will be some cases where we have absolute maximums and minimums, but in this case we don't. Briefly want to talk about concavity. So if something is concave up, that means that it's opening upward. We talked about parabolas yesterday and how they can look like this, or how they can look like this. This parabola would be an example of concave up. This parabola would be an example of concave down. Now, if we just hid all of this part of the parabola and just put our hand over this part, the only part of the it's not a parabola, of this function. The only part of the function we'd see would be this part. And that part of the function is concave up. But then if we were to put our hand over this part of the function is concave down. So it is concave up for some of the function, and then it's concave down for the rest of the function. So what I'm going to do is, it's going to be inexact, but I'm going to make a point right here that is just me saying this is about where that concavity is shifting. So that concavity shifts at this point 1, 7. So what I'm going to say is that my function is concave up all the way until we get to there, right? And everywhere in this direction, it's also going to be concave up. And then after that point, from that point on, then it's concave down forever. So we're going to make a statement about that interval. What we're really saying is that the x values, when it's concave up, so concave up, our x values are between negative infinity, that's everywhere in this direction, right? Because we can't say that it ever ends, because this function continues forever and ever and ever. Between negative infinity and then up to 1, because that's the x value here where the concavity shifts. But then it's going to be concave down, starting at 1, and then it's concave down forever. Okay? So that's notation for describing where this function is concave up or concave down. Just so you're aware, this is not something that's going to be big in Algebra 2. It's going to be something that comes up later in your math lives, but it's important that you're aware of the concept of concavity at this point and the concept of writing x in these intervals and describing the domain of the function. So that brings us to our next point, which is what is the domain of this function? So we just quickly have to define domain. The domain of a function, and I'm sure you're aware of it because this is something that's been talked about, domain is all possible inputs. And when we're talking about inputs, we're talking about x values. So what are all the possible x values that I could put into this function? It's a very simple question, really. Could I put a 0 into this function? Yes, it exists at 0. Could I put a 2 into this function? Yep, the function exists at 2. I could put a negative 2 into this function too, right? Because these arrows are showing me that it continues forever, so it will eventually have a value at negative 2. Because of these arrows, this function exists everywhere in my domain. It exists for every single real number that my x values could be. So we'll say that our domain is all real numbers. That's what that means, all real numbers. All right, so let's talk about range now. If domain is our inputs, then range is our outputs. So that's just us saying, what are the possible outputs I could get from this? This is a little trickier of a question to ask. So let's start with, is it possible for me to get an output of 5? So 5 is right here. It looks like it is possible for me to get an output of 5 because if I use an input of 0, or if I use an input of 3, I'll get an output of 5. So that would mean 5 is in my range. It looks like 9 is also in my range. I see that 6 is in my range, 8 is in my range, 10 is in my range, 12 is in my range, and any number above will be in my range because it moves upward towards infinity. And the same is true when I'm headed in the negative y direction. All of my negative values are in my range as well. So we would say that our range is also all real numbers. And that's something that we're going to get a lot deeper into. All right, guys, I'm trying to keep these videos under 10 minutes. So what we're going to do with this one is with these 2 practice problems here, I am going to encourage you guys and ask that you do A and B on your own, okay? So give it a shot before we get to class. Remember, all we're looking for here are critical values. So that's just 2 things, right? That's just maximums and minimums and roots. So in order to get those critical values, I'm not asking you to do any algebra yet. I'm just asking that you graph these functions and look at those critical values and just state them. So when you do that, you'll just go to desmos.com, type in each of these functions, and then write down what the roots are and what the maximums and minimums are, okay? This piece here, domain and range, we will talk about when we get to class. So when we get to class tomorrow, we'll finish up by quickly going over A and B, and then we'll talk about domain and range and start practicing. All right, so I do know that this is a longer video than you guys are used to, and then it'll be in the future. So bear with me, but this is a pretty dense lesson. So good luck with this, you guys, and I will see you all tomorrow.